In this video, we'll be covering u substitution given that the integral is going to have some bounds on it. So this first example right here, the integral from 0 to 1, x parentheses x squared plus 1 to the power of 2 dx is, you'll notice here that the interior is x squared plus 1. And yes, I suppose that you could take x squared plus 1 to the power of 2. You could FOIL that all out and you could distribute the x in. But what if this power happened to be, say, 5, 10, 20? There would be not a nice, efficient way to evaluate that algebraically before we attempt to take its antiderivative. So what we're going to do instead is we're going to go ahead and use u substitution. Off to the side here, I'm going to write u equals, and the u that I'm going to let be is x squared plus 1. And the reason why I'm going to let it be that stuff is because you'll notice that it's in the interior of something squared. Now keep in mind, remember, every time that you attempt to use u substitution, you might not get the correct u right off the bat the first time. But it's important for us to attempt different u's. I'm going to go ahead and again start with just what's in the parentheses. I'm not going to do that squared function, although I could attempt it. I could let u equal be all this plus the squared on top, in which case, again, it might not work out. But it wouldn't be a bad idea to try it. So now, my du, given that my u function is x squared plus 1, is going to be 2x, and don't forget again, always attach that dx to the end, because again, we're taking a derivative of this function, and we're moving the differential of dx over. So now you'll notice that I have 2x dx, and outside here I have an x, I have a dx, so all I'm missing is a 2. So I'm going to put a 2 over 2 inside of that integral, or outside of that integral. I'm going to pull this 2 on top into that integral. So you'll notice here so far we have done nothing new with this integral. So again, I'm going to have a 1/2 sitting on the outside. I'm going to have 2x, the x squared plus 1 to the power of 2 dx. The 2x dx is my du, and this inside right here, x squared plus 1, becomes my u. So this integral is 1/2, and this is where it's important that we make note of this. X equals from 0 to 1 of u to the power of 2 du. The reason why it's important for us to make note that this is x equals is because, yes, we could change the bounds on this integral and change the bounds such that they're in terms of u. Now, in all previous examples, we've always taken this, we've done the integral, and then we've back substituted x into the problem. I'm going to go ahead and do it that way this first time, but you'll have to make note that, again, there is another way to do this problem where we change the bounds and we don't back substitute. So, in this next step, I'm going to go ahead and integrate this function. I'm going to go 1/2, the integral of u squared is u to the power of 3 divided by 3. This thing is going to be evaluated from x equals 0 to 1. And again, because it's evaluated from x, it means that we can't plug those values into this integral, or evaluated integral, just yet. We have to make sure that we back substitute what u really is. So in this example, I'm going to have 1/2. I'm going to have x squared plus 1 divided by 3. But that x squared plus 1 is to the power of 3, still evaluated from x equals 0 to 1. And again, it's important that we write the x equals from 0 to 1. Otherwise, we're going to confuse the variable that we're allowed to be plugging in to this integral, or, again, already evaluated integral. So now in our last step here, we're just plugging in the values. If I were to plug in 1 to this integral, I'm going to have 1/2 times a 1/3, which is a 1/6. I'm going to have 1 squared, which is 1, plus 1 is 2, 2 to the power of 3 is 8, and I will end up having something along the lines of 8 over 6. Again, this is me plugging in 1. That rule doesn't change. I still do plugging in the top bound first, minus plugging in the bottom bound second. So when I plug in 0, I'm going to have 1 to the power of 3, which is 1. 1 over 3 times 1 over 2, which is 1/6. So now I have 8/6 minus 1/6, which is nothing more than 7 over 6. And that is the final result for that particular problem. Now, if I backtrack again one more time, if I backtrack to about here, I'm going to go ahead and make an off turn, and we're going to talk about how I would make this integral be all in terms of u without having to do any back substitution. So I'm going to have 1/2, the integral from x equals 0 to 1. But what I'm going to do is back up here, where I have u equals, is if x equals 0, u is going to be equal to 1. And again, make note of that. If I plug 0 into this function, I'm going to have 0 squared plus 1, which is just 1. And if x equals my 1 value, again, notice I'm using 0 because that's the lower bound. I'm using 1 because that's the upper bound. If I plug in 1, then u is equal to actually 2. Again, 1 squared plus 1 is 2. So now I can go ahead and change my bounds to be from 1 to 2 instead of from 0 to 1. And this thing is going to then equal to 1/2 u to the power of 3 divided by 3, evaluated from u equals 1 to 2. And then I can simply plug those values in. I don't need to do any back substitution. Now, if we did anything wrong, we won't get the same answer. But if everything is right, we should get the exact same value we got here. You'll notice if I plug in 2 first, I get 2 cubed, which is 8. 8 over 2 times 3 is 8 over 6. Minus, again, this is plugging in f of 2 in this case, minus me plugging in f of 1, plugging in the bottom bound. I'm going to get 1/3 times 1/2, which is simply 1/6, and once again, I get 7 over 6. So again, you'll notice that both of these are exactly the same, and you can either, for these examples, back substitute u, or you can transition all of your x's, including the bounds, to u. This does not work for every example. For any example that doesn't have bounds, you must back substitute for what x was. Otherwise, your answer is going to be in the wrong notation or form.